Uh, Today we will see the Galerkin's approach to the one dimensional finite element problems, and in the Galerkin's method we have already seen that this is the equation that we get for the virtual work done, that is this part is the virtual work done against the internal forces and this is the external virtual work done, and we said that the two will be equal in magnitude and the total virtual work done will be 0. Okay, this we have already seen. Now if we talk of one dimensional problems, we formulated one dimensional problem like this, that if we take a body like this, we are splitting it into a set of 1D elements like this, and if you take any individual element of uniform cross section having two nodes 1 and 2, we said that this has a displacement given by q1 q2, or the element displacement vector we said was q1 q2, which we are representing as the vector q or the matrix q. Okay. Now in this Galerkin's approach we are giving it a virtual displacement. So if we give this a virtual displacement, let us say the virtual displacement at this end is phi 1 and the virtual displacement at this end is phi 2. Okay, and we will make a virtual displacement vector just like this, which will be phi 1 phi 2 transpose, and we will call that, let us say, the matrix psi. Okay. If you use this, and we want to find out the virtual displacement at any point inside this element. Okay, if I take any arbitrary point here, if I want to find out the actual displacement, we have written the equations earlier. We said u will be equal to n times q. Okay, where n is nothing but n1 n2. Okay, where n1 and n2 are the shape functions. So we have said u is equal to n times q. Similarly, if we want to find out the virtual displacement at any point inside this element, let us say the virtual displacement here is phi, we will again say that this phi will be a linear combination of phi 1 and phi 2. Okay, so we will say phi will be equal to n times psi, or this is the same as n1 phi 1 plus n2 phi 2. Okay, this u equal to nq, that is the same as n1 q1 plus n2 q2. Okay, so we will say phi will be equal to n times psi. Okay. The next step, if you notice, the first term that we have here has a term of epsilon of phi, and we said that this epsilon, this strain, is the strain that will be caused by the virtual displacement that we are giving. Okay, so this strain caused by the virtual displacement will be nothing but d phi by dx. Okay, that is, if you look at the actual strain, this I am saying is epsilon of phi. If I look at the actual strain, epsilon, that is equal to du by dx, and this we had derived last time. If I differentiate this equation, I will say this will be equal to b times q. Okay, similarly, if I differentiate this, phi equal to n times psi, I will get this will be equal to b times psi. Okay, and this derivation is straightforward. All that I have to do is differentiate n1 and n2 with respect to x. Okay, and this matrix B is the matrix given by this expression. Okay, this matrix B is the same as the matrix here that we had, and the derivation for this is also absolutely the same. Okay, so epsilon of phi will be equal to B times psi, and epsilon is equal to B times Q, and if we say epsilon is equal to B times Q, we can say sigma will be equal to E times B times Q. Okay, where E is the Young's modulus, B is the element strain displacement matrix, and Q is the element displacement matrix. Okay, so we have an expression for sigma and we have an expression for epsilon of phi. If I take these two expressions, I can put them into the first term, that is this term, which corresponds to the internal work done, and if I expand this term for the internal work done, my first term here which is the volume integral of sigma transpose epsilon of phi dV. Okay, this will be equal to sigma is equal to EBQ. So sigma transpose will be equal to Q transpose B transpose multiplied by E, which is a constant anyway. That's not a matrix. Okay, so I'll put that over here. So this will be equal to the integral of E Q transpose B transpose multiplied by epsilon of phi. Epsilon of phi is B times psi, so I'll put that over here, B times psi dV, which is a differential volume element, that will be equal to area times dx. So it will be area of the element multiplied by dx, and now this integral will be integral over the length of the element. Okay, and now in this you will notice that E is a constant, Q is a constant, B transpose B and psi and A, they are all constants. Okay, they do not change with x, and dx, the integral of dx is nothing but the length of the element. Okay, so if I put all these values here, this will be equal to E into A multiplied by integral of dx, which will give me LE, multiplied by Q transpose B transpose B psi okay. Now again B transpose B is this expression, so B transpose will be 1 over LE into minus 1 1. Okay, so I'll put these values over here. This will be equal to, I'll get Q transpose into E A LE into 1 over LE multiplied by minus 1 1 into 1 over LE multiplied by minus 1 1, and this whole thing will be multiplied by psi. Okay, this will be equal to Q transpose into E A over LE. I have LE squared in the denominator and LE in the numerator, and the product of these two matrices will give me 1 minus 1 minus 1 1. Okay, so this thing will be again multiplied by psi. Okay, and now this expression is the same as the expression for Ke, which is a stiffness matrix. Okay, so this will be equal to Q transpose into Ke into psi. Yeah.
So what is Q and what is psi then?
What is Q and what is psi?
The psi we have defined as phi 1, phi 2 virtual displacement.
Yeah.
So
Q is the actual displacement. See, this is my element. At this point 1, the actual displacement is Q1. At this point 2, the actual displacement is Q2. In addition to that, I am giving a virtual displacement, which is phi 1 and phi 2. Q1, Q2 give me a vector which is Q. Phi 1, phi 2 give me a vector which I am calling as psi.
But strains we have found out using psi.
See, using psi I found out what I am calling epsilon of phi. The strains which will be caused only due to the virtual displacement. Okay, the actual strains because of the loading, they are epsilon, which is nothing but du by dx. Okay, the strains caused due to the virtual displacement are d phi by dx. Okay, so when I give it a virtual displacement, the effort involved in giving a virtual displacement will be doing some work against the internal stresses. Those internal stresses are actually the stresses caused by the loading. Okay, that internal work done is this term. Okay, that is why I have a term of the actual stresses multiplied by the strain caused due to the virtual displacement. Okay, the product of the two integrated over the volume will give me the work done. Okay, so this internal work done is equal to Q transpose Ke into psi. This is the internal work done within the element. Okay, any questions up to this point? Okay, now if you look at this expression for the Galerkin's method, the first term we have simplified. Similarly, we will simplify the other terms. Okay, and then we will try to get a set of equations for solving for Q using this general equation. Okay, so let us take up the second term now. The second term is integral of volume integral of phi transpose into F into dV. Okay, now if I take up this, again phi is equal to n times psi. Okay, I am writing it directly. So phi transpose will be psi transpose multiplied by n transpose. Okay, F is the body force within the element, dV is A times dx. A is the area of cross section in the element. Okay, and again now this integral will be over the length of the element. Okay, so this will be equal to psi transpose is a constant, F is a constant, A is a constant. So this integral will give me psi transpose into integral of n transpose dx, and this whole thing is multiplied by F and A. Okay, this integral is over the length, and the integral of n transpose dx, we have derived this integral earlier. I will quickly repeat it here. Psi transpose, n transpose will give me a column vector of n1 n2, integral of that with dx, and this column vector we have multiplied by F A. Okay, and again if you remember integral of n1 dx, it said earlier that n1 is a shape function which along the length of the element is changing from 1 to 0 like this. At the point 1 it is equal to 1, at this point it is equal to, at the point 2 it is equal to 0, and the integral n1 dx will be the area under this curve, and this integral is equal to LE by 2. base into height into half. Okay, if we put that over here, this will be equal to psi transpose into LE by 2 into 1 1 into F A. Okay, so this is again equal to psi transpose into F A LE by 2 into 1 1. Again we get a result which is very similar to what we had last time, that is when we are using the Rayleigh-Ritz method, that F A into LE is the total body force acting on the element. F is the body force per unit volume and A into LE is the volume of the element. So this is the total body force acting on the element. So we are saying half of that is acting on the first node, the other half of that is acting on the second node. Okay, and this we can write this as psi transpose into, let us say, a body force vector Fe, and effectively it means that if we have an element like this, the total body force that is acting will split it equally into two parts, one acting on the first node, the other acting on the second node, and the virtual work done will be the virtual displacement of the first node into this force plus the virtual displacement of the second node into this force. That is the virtual work done against the body force acting in this element. Okay, so this term can be simplified into psi transpose times Fe. Okay. So again, if you look at this expression, this term, again we have simplified this now. Similarly, we can simplify this term also. Okay, and I will leave it for you to derive this, that this term, which is integral of phi transpose T ds, the surface integral of this will be equal to psi transpose times Te, where Te will be equal to T times Le, which is the total tractive force acting on the element, divided by 2, and that would be split equally between the two nodes. Okay, so effectively the total tractive force will also be split equally between the two nodes. Okay, so the third term, this term will evaluate to this expression. Okay, and if you notice, the terms that we are getting are quite similar to the terms that we had in the Rayleigh-Ritz method, except that there instead of psi we were having q. That is the only difference. Okay, so now if I take up this complete expression, what I will get will be, I will just rewrite the same thing first, sigma transpose epsilon of phi dV minus volume integral of phi transpose F dV minus surface integral of phi transpose T ds minus sigma phi transpose P is equal to 0. Okay, now this is the integral over the complete volume. So integral over the complete volume will be the same as summation over the integral of each of the elements. Okay, so this would be, this expression will give us, if I do a summation over each of the elements of the integral for each element, okay, that will be the integral over the element sigma transpose epsilon of phi dV minus summation over all the elements into the integral over the element of phi transpose F dV minus summation over all the elements integral over the element surface area phi transpose T ds minus summation of phi transpose P will be equal to 0. Okay. Now this term is what we have just shown to be Q transpose Ke times psi. Okay. So this will give me summation of Q transpose Ke times psi minus summation of this term is what we just derived as psi transpose times Fe. Okay. So it's a minus summation of psi transpose Fe. This term is what we have just mentioned over here, minus summation of psi transpose times Te minus summation of phi transpose times P equal to 0. Okay. And again Ke, that is the stiffness matrix, is a symmetric matrix. Okay. So just for the sake of convenience, what we will do is this term Q transpose Ke psi, I will write that as, what I am saying is Q transpose Ke times psi, this is the same as psi transpose Keq. Okay, because Ke is symmetric and I can take a transpose without changing anything. Okay, this product of these three is just a single number. If I take the transpose, I will get this. Okay, so this is the same as this. Okay, so I will use this expression from now onwards, and what we will get this thing will now become summation of psi transpose Ke times Q minus summation of psi transpose Fe minus summation of psi transpose Te minus summation of Q phi transpose times P. Okay, now if I look at these three terms, in each of the three terms I have a force matrix. This is a force matrix multiplied by the virtual displacement. This is also a force matrix multiplied by the virtual displacement, and here I have got point forces multiplied by the virtual displacement at that point. Okay, so just as we did earlier, I can combine these three terms into one single force matrix. Okay, so this is equal to 0. I can rewrite this as summation of psi transpose Ke times Q minus summation of psi transpose F. Okay, where this F is the element body force matrix. Okay, and I will say this will be equal to 0. Okay, and if I follow the same method as I did earlier for converting this element matrices into the global matrices, I can say that this is the same as writing, I will convert this psi into a global matrix phi, this Ke into a global matrix K, and this Q into a global matrix Q. Okay, and this again will be minus this psi I am changing to a global matrix phi, and this F is I am changing that into a global force matrix, and I will say this is equal to 0. Okay, where this global force matrix phi will be equal to phi 1, phi 2 till phi n if I have n elements. Okay, the definition of K, Q and F will be the same as what we had earlier. Okay, this global matrix K will be assembled from the individual stiffness matrices just like we did earlier. Okay, the global force matrix will be assembled from the individual force matrices and the point loads just as we did that earlier. Okay, so we will get this this equation for the Galerkin's approach. Okay, and this I can write that as phi into KQ minus F will be equal to 0. Okay, where phi is the global matrix of virtual displacements, Q is the global matrix, Q will be equal to Q1, Q2 till Qn transpose as a global matrix for deformations, F is the global force matrix, K is the global stiffness matrix. Okay, so we will get phi into KQ minus F will be equal to 0. Okay, and this is the equation that we will be using for the Galerkin's approach. Okay, and we have already said that as per the Galerkin's method, this equation has to be satisfied for all values of phi. That means whatever be the virtual displacement I give to the system, this equation should be satisfied. Okay, that means any virtual displacement which is consistent with the boundary conditions. Okay, if you remember earlier we said that in the Galerkin's approach, the first thing we were saying was that phi has to take the same form as Q, that is the virtual displacement and the actual displacement should have a similar description. Okay, and that we have ensured by saying that Q is equal to Q1 Q2 transpose and psi is equal to phi 1 phi 2 transpose, and by saying that phi is equal to n times psi and u is equal to n times q. So you are taking a similar formulation for phi as well as for u, and the other constraint is that this phi has to be kinematically admissible. That means this has to satisfy the boundary conditions. We can only give it a virtual displacement which is consistent with the boundary conditions. Okay, so if we keep this constraint in mind, then this equation has to be satisfied for all values of phi. Okay, so this equation we can use for solving for q. So if it has to be satisfied for all values of phi, we can essentially say kq is equal to f and then attach the boundary conditions to that. Okay, if we attach the boundary conditions to that, we will come back to the same equations as we had with the Rayleigh-Ritz method. Okay, so essentially we will see that whether we use the Rayleigh-Ritz method or the Galerkin's approach, the final equation that we are getting, they will be the same. Okay, sorry, the final expression for the stiffness matrix, force matrix, and the resulting values that we will get for q, they will be the same irrespective of whether we use the Rayleigh-Ritz method or the Galerkin's approach. Okay, any question on the Galerkin's approach? Okay, so essentially if you look at the method that we are using for the one dimensional problems, let us say in the Galerkin's approach we started with this equation, okay, then we simplified this first term and we got an expression like this. Okay, an expression like this. Sorry, this is the second term. For the first term we got an expression like we got this expression. Okay. For the second term we got this expression, and a similar expression we got for the third term. Okay, that is for this term. Okay, now whether we have one dimensional problems or two dimensional problems or three dimensional problems, our aim will always be the same. We will take expressions like this, simplify them using a set of shape functions. Okay, what we have done is we took a set of shape functions as we had an element like this, which is a one dimensional element, and we said that we will take two nodes on this element, 1 and 2. If we specify the displacements at these two, q1 and q2, we will find out the displacement at any arbitrary point by taking two shape functions n1 and n2. Okay, we say u will be equal to n times q, where n1 and n2 are two shape functions. Okay, those shape functions are basically deciding the contribution of q1 and q2 at this point. Okay, and then we are using this formulation to simplify this expression as well as this expression. Okay, and we finally simplify these expressions to simple matrix products. Okay, and those matrix products are again in terms of q's. Okay, now whether we have one dimensional element, 2D elements or 3D elements, our approach is going to be the same. Let us say in 2D we will try to take either triangular elements or quadrilateral elements, maybe with 3 nodes, 4 nodes, okay, or higher number of nodes. Have shape functions for each of these nodes, and using that we will simplify this, and finally the expression that we will get will be the same expressions, psi transpose times Fe or this expression, okay, or there will be expressions of this type. The final expression will always be the same, okay, irrespective of what is the shape of the element we are choosing. Okay, our aim will be that the final expression should be the same. So basically when we say that we will take a particular type of element, that is triangular or quadrilateral with 3 nodes, 4 nodes or 6 nodes or 10 nodes or whatever, we will finally come to the same set of equations. The only thing that will be different will be how to get k and how to get f. Okay, we will take different shape functions with every element and we will get different methods of assembling the K matrix and assembling the F matrix. But once the K and the F matrices have been assembled, a method of solution is going to remain the same. Okay, and the method of solution is one method that we have seen, that is elimination approach, and we have one more approach that is called the penalty approach. Okay, so let us briefly see the penalty approach and then we will see an example of the penalty approach maybe in the next class. Okay. Now, when you are talking about the penalty approach, this is for solving the system of equations. Okay. If we look at the potential energy expression that we had earlier in the Rayleigh-Ritz method, we said that the potential energy pi will be equal to half of q transpose k q minus q transpose f. Okay, and for this we had let us say some body, and on this body we are considering some constraint that some node over here is fixed or has a fixed displacement. Let us say this is node number 1, and again we will consider the constraint that Q1 is equal to A1. Okay. So, what we will do is we will approximate this body by a body like this. We will add a spring at this location. This spring has a spring constant of C. Okay, and this node is 1, the rest of the body is the same. Okay. Now, if I give this end a fixed displacement equal to A1, okay, and the displacement of this end of this node, that is node number 1, that is Q1. Okay, the deformation in the spring delta will be how much? Q1 minus A1. Okay, because A1 and Q1 will be in the same direction. Okay, so the actual deformation of the spring will be Q1 minus A1. Okay, and the potential energy stored in the spring, that will be equal to, let us say, the U of the spring will be equal to half kx squared, which is equal to half C into Q1 minus A1 whole squared. Okay, so now if I look at this complete system, the potential energy in this complete system would be this potential energy, okay, plus the potential energy of this spring. Okay, so now my complete potential energy, I will write that as pi, which will be half C into Q1 minus A1 whole squared plus half Q transpose K Q minus Q transpose F. Okay, and essentially what we will say is that if I take this spring and I make this spring very stiff, okay, as C approaches infinity, this system will approach this system. Okay, as this spring becomes very stiff, this system will be almost the same as this system. Okay, because then I will essentially get Q1 equal to A1. Okay, but this spring is so stiff that whatever deformation I am giving to this end, Q1 will also go through the same deformation. Okay, so we will now solve for this system, okay, and then take the limit as C tends to infinity. Okay. So I have this expression, again I will write this as half of C into Q1 minus A1 whole squared plus, I will expand this term, which is half of the same as what I had written yesterday, Q1 K11 Q1 plus Q1 K12 Q2 plus so on up to Q1 K1n Qn plus Q2 K21 Q1 plus Q2 K22 Q2 Q2 K2n Qn. minus q transpose time f, which will give me q1 f1 plus q2 f2 okay. So this is the expression we have for the potential energy. If I take this expression and again apply the constraint that del pi by del qi is equal to 0. Okay, so first I will differentiate with respect to q1 and I will get del pi by del q1, and what will that be equal to? When I differentiate this with respect to q1, I will get this term multiplied by 2, I will get this term, so on up to this term, and in this column I will get this term, so on up to this term. Okay, just as plus I will get differential with, when I differentiate with respect to q1 I will get a term from here. Okay, so the term from here will give me c times q1 minus c times a1. Okay, the terms from here will give me this plus k11 q1 plus k12 q2 plus k13 q3 so on up to k1n qn. Okay, and then this term will give me minus f1. Okay, so this minus f1 will be equal to 0. Okay, similarly when I differentiate with respect to q2, I will get this term, I will get 2 times this term, I will get this term and so on, and on this side I will get this term, so on, and this term. Okay, just like we differentiated last time. Okay, and this is going to give me expressions like k12 q1 plus k22 q2 plus k23 q3 so on till k2n qn minus f2 is equal to 0 and so on. Okay, so this way we will get a system of n equations. Okay, now we have n equations, not n minus 1 equations. Okay, because I am also differentiating with respect to q1. Last time I had put q1 equal to a1 and I had eliminated the variable q1. I am not doing that now. Okay, so I will now have a system of n equations, and if I write them in a matrix form, in this equation, in the first equation, my coefficient of q1 is c plus k11. Okay, and all the other terms have coefficients which are the same as the stiffness matrix, k12, k13, k1n and so on. Similarly in this equation all the coefficients are k12, k22, k23 and so on. Okay, so when I write it in the matrix form, it will become, the coefficient of q1 is k11 plus c. Okay, so the first term here will become k11 plus c. The coefficient of q2 is k12. Okay, the other terms will remain the same, k12, k13, so on till k1n. If I take up the second equation, I will get k12, k22, k23 and so on. Okay, so this will become k12, sorry, k21, k22, k23 and so on up to k2n, and this will continue. We will get kn1, kn2, kn3 up to knn. Okay, and this thing is multiplied by q1, q2 up to qn, and this will be equal to the first term here is this f1 and c times a1. Okay, so the first term here will become f1 plus c times a1. The first term here is only f2. The second term will be f2, and all the other terms will be the same. Okay, so this is a system of equation that we will now get. Again, this again we will write it in a similar manner. K prime q prime will be equal to f prime, but now k prime is obtained by taking the same n by n matrix, but in the diagonal element I am just adding the stiffness of the spring that I have taken, C. Okay, and f prime I am getting by just adding C times A1 in the first term in the first location. Okay, so this is the system of equations that we will have, and in this system of equation, as I take the value of C to be very large, if I take C to be very large, I will finally approach the case where Q1 will be equal to A1. Okay, we can see that mathematically also. Okay, so in this penalty approach, what we are doing is we are taking the stiffness matrix, and in the diagonal element for the constraint which is for the node which is constrained, we will add a very high stiffness, very high value C, and corresponding first term will modify it by adding C times A1. Okay, mind you, we are talking of a constraint which is Q1 is equal to A1. Okay, so I am taking a very high stiffness C, adding that in the stiffness matrix, and adding C times A1 in the force matrix. Again, then I can solve the system of n equations and get the different values of Q1, Q2 till Q1. Q prime is the same as Q. Okay, so this is the penalty approach. Okay, next I will take a small example of this penalty approach and then see how it can be used. Okay.